Motor starter troubleshooting part 2. In this presentation, we're going to look at a specific phenomena that can occur while troubleshooting motor control systems. And it has to do with overcurrent situations. As we all know, when a low impedance path is established across two terminals of an energized source, high current will flow, or a short circuit. What should occur with that high current is that the overcurrent, which is protecting the wire, should trip. Now, there's two different types of short circuit conditions. One of them is known as a line-to-line short circuit, and that's where the short circuit is established between two of the ungrounded phases of the source. The other is a ground fault, and usually we're working with a Y system that's solidly grounded, which means one of the ungrounded conductors coming into contact with metal or earth or the neutral will cause a short circuit, but it's known as a ground fault. If the control circuit is transformer supplied, one side will be grounded. If a ground fault then occurs on the grounded circuit conductor in the control circuit, no overcurrent will trip, nor will there be any issue with the operation of the circuit. Even if insulation becomes frayed and damaged, perhaps we could have a little bit of arcing, but it's not going to cause the overcurrent to trip because all of the current travels back here to the bonded connection on the secondary of my transformer. There is the possibility of heat sparks developing due to this flow of current through the metal conduit boxes and back to the control source. However, again, the overcurrent will not trip. If a ground fault occurs on the ungrounded circuit conductor in the control circuit, a short circuit will be established, tripping the control overcurrent. So in this example, we would have a path back to the secondary side of my transformer, and the fuse should blow. If a ground fault occurs on neither a grounded or an ungrounded control circuit conductor, nothing will occur until the conductor is energized, such as this situation here. One of the conductors, perhaps the conductor at location 5, has some insulation that's been compromised and is now in contact with the metal of the conduit that it's installed within. Nothing happens until the up push button is depressed down. And at this point, we create a short circuit by pressing the push button. We have a short circuit back to the secondary of the transformer. And in addition to looking at the insulation on the conductor where location 5 is, we would also want to look at all of the other equipment that the control circuit short circuit flowed through. It's likely that due to the very low current rating of all of the equipment, the push buttons and the interlock and the overload contact, they're probably all rated for 120 volt max and a current of perhaps half an amp. On these devices, it's highly likely that they will now be damaged and welded into the closed position, unable to operate. When we look at different types of control circuits, different situations can arise. This again is another grounded secondary 120 volt motor control circuit. However, you'll notice that the overload has been located on the right-hand side. In this particular situation, what you want to consider is what would happen if a ground fault were to occur at location K while the motor is running. In this situation, well, nothing would happen, as in the motor would continue to operate, no overcurrent would pop, and there would be no sort of danger to the overall system. However, will the motor shut down if the overload contact were to open due to an overload condition of the motor? And the answer would be no. No, the motor would not shut down. If we have a ground fault at location K, that means that the current is bypassing the overload contact and thereby making a dangerous situation where that contact now becomes inoperable in the overall system. So odd things can occur depending on how the control circuit has been set up. If a ground fault occurs in the power circuit, the affected line will cause a short circuit, such as we see at the very top in phase C. We would have a short circuit back to the source, and the fuse would blow. Keep in mind that if this was a breaker setup with 3-pole breaker for 3-phase application, all 3 of the lines would trip simultaneously. In a fusible disconnect, only the fuse that has a short circuit will open, and in this situation, the motor would then be running single phasing, so higher current and overloaded. If a ground fault occurs in the power circuit leading down to the control circuit, again, the offending line will cause the fuse to blow. Line-to-line short circuits are where we have 2 affected lines, and they are typically much higher in energy and in explosive force. So when we have a line-to-line short circuit, it's highly probable or more probable that we will have damage to the equipment. In this situation, I have a line-to-line short circuit between A and B. Both the fuses should pop. I can also have a short circuit in a transformer. At times, the windings can fail or a foreign object can get wedged into different positions within the transformer itself. If we were to have a short circuit across H1 to H4, the 2 closest overcurrents should trip first. However, due to the way that selective coordination has been designed with the system, we might see the 2 A and B fuses in the main power circuit blow as well. We can also have a short circuit on the secondary of the control transformer. In this situation, we would expect to have a short circuit running, or the current value flowing through the primary that is very high, and again, blown fuses on both the left and right side of the primary of my control transformer. At times, it can be important to understand what would happen when a wire were to break. Although not the most common situation when it comes to troubleshooting, it still can happen due to vibration or loose connections. We have a broken wire in phase C connecting right to the motor at the junction box. If this were to break while the motor is running in the up position, it means that eventually the overload will probably trip because the motor is single phasing. If the wire is broken in this location and the operator presses the up button, it means that we will have 0 happening in the system. Oh, you know what? I should go back a moment. Let's go back to this one. Wire is broken. Operator now pushes start up button. I wasn't even reading what I typed. So the wire's broken, and if we start the motor, it's highly likely that in this single phase condition, it will not have the torque available to get going and start. So what you might end up hearing is the motor trying to start, but due to the load on the shaft is unable to, and it will hum. It will hum and it might turn a little bit, and then the overload will trip. So kind of interesting to know. We already looked at this one. What about that one? Wire's broken here. Operator presses the start up button. Well, nothing's going to happen, and that's because we have no power. And finally, what if the wire breaks in the holding circuit of the up portion? Well, when the operator presses the up push button, the motor should start, and whatever this happens to be, it's a garage door opening circuit. The door should start opening. However, as soon as they release the up push button, the motor will stop. And that's because the holding contact that's in parallel with the up push button is not going to be connected back here to terminal 4.